In this lesson, we will discuss the history of the development of liquid crystal displays, which are widely used today in computers, mobile phones and flat-screen television sets. It is a technology that combines chemistry, physics, and engineering. A liquid crystal is a chemical compound that exhibits a unique state of matter between a crystalline solid and a flowing liquid. It is known as the liquid crystalline state. The liquid crystalline state was discovered by German botanist Friedrich Reinitzer in 1888. This is a photo of a large drop of liquid crystal material on a glass plate. The liquid crystalline state has an opaque appearance. A thin layer of a liquid crystal material on a glass plate is shown in this photo. Note the thread-like appearance. The Greek word for thread is nematos, so this type of liquid crystal is called a nematic liquid crystal. The arrangement for the molecules in the liquid crystal state is different than in the solid state or the normal liquid state. In the crystal state, the molecules are aligned parallel to each other, and held firmly by their sides, as shown in the diagram. The molecules cannot slide past each other because of this rigid arrangement. When a liquid crystal material is heated from the solid state, it forms the liquid crystalline state at a very specific temperature. In the liquid crystalline state, the molecules are still parallel to each other, but they are no longer held rigidly by their sides as shown in the diagram. When a liquid crystal material is further heated from the liquid crystalline state, it will form the normal liquid state at a very specific temperature. The normal liquid state is called the isotropic state, and the diagram shows that molecules are free to move about in all directions. This diagram shows how the molecules in the liquid crystalline state are ordered. The molecules act as dipoles, being positive at one end, and negative at the other. The attractive forces hold the molecules close together by their ends, with the negative end of one molecule attracted to the positive end of another. Because the attractive forces are much stronger at the ends of the molecules than at their sides, the molecules can slide past each other. This diagram shows the structural formula of a liquid crystal molecule. This compound is called hexyl cyanobiphenyl and it exhibits the liquid crystalline state over a narrow temperature range from 15 degrees Celsius to 29 degrees Celsius. Note that the shape of the molecule is similar to an ellipsoid. The carbon-nitrogen group on the right end is called electronegative, meaning it draws electrons from other parts of the molecule. This gives the molecule its dipolar nature, with the negative end on the right and the positive end on the left. Now let us look at how the liquid crystalline state forms from the solid state and how it converts to the normal liquid state. If we take cold crystals of hexyl cyanobiphenyl in a test tube and heat the tube to 15 degrees Celsius, the crystal will melt to form the opaque liquid crystalline state. If we continue heating the tube, the opaque liquid will turn completely clear at 29 degrees Celsius. When we cool the clear liquid, it will once again form the liquid crystalline state, and precisely at 29 degrees Celsius. On further cooling, the solid state will form precisely at 15 degrees Celsius. There is no change to the chemical structure of the material, so these changes represent a completely reversible physical change. The changes in the states of matter for the compound hexyl cyanobiphenyl are shown in this video. A heat gun is used to heat the tube.
This is an aerial photo of the David Sarnoff Research Center in Princeton, New Jersey, where the first liquid crystal display was developed in 1966. This facility was the central research center of the RCA Corporation at that time. Today, it is part of SRI International, an independent research and development organization. RCA developed the first color television in 1957. In the early 1960s, it was searching for a way to develop a flat thin television display to replace the bulky and heavy cathode ray tube then in use. On the left is a photo of the cathode ray tube that was used in television sets from the product's creation in the 1930s. On the right is an artist's conception of the flat panel television that the company envisioned for the future. Liquid crystals were chosen as a promising material for the development of flat-screen displays when Dr. Richard Williams, a physical chemist at RCA Laboratories, discovered that a low-voltage electric field caused a pneumatic liquid crystal to change its optical properties. Dr. Williams suggested that this material might be used to make a flat-panel television screen. In his first experiment, Williams reported that a liquid crystal changes its optical properties in a low-voltage electric field. The formation of the pattern shown in this photo that he observed became known as Williams domains. Williams' discovery caught the attention of physicist Dr. George Heilmeyer, who formed a group to develop a display based on liquid crystals. The original group, shown in the photo, included Lucian Barton, Joseph Castellano, George Heilmeyer, Joel Goldmacher, and Louis Zanoni. This simplified diagram shows the motion of liquid crystal molecules in an electric field. This cell consists of two glass plates coated with transparent electrodes on its inner surfaces, with the liquid crystal sandwiched between the electrodes. Note that the elliptically shaped molecules line up parallel to the electrode surfaces when the power is off. With the power on, the molecules line up perpendicular to the electrode surfaces. Actual displays are much more complicated, and involve special treatment of the electrode surfaces as well as the selection of the liquid crystal material and other components. One of the first discoveries was made in 1965 by research physicist Dr. George Heilmeyer, who demonstrated a flat thin device using pneumatic liquid crystals in a low-voltage electric field. He called this phenomenon dynamic scattering. This photo shows an early demonstration of the effect. In their experiments, Williams and Heilmeyer both used a material that had to be heated to 90 degrees Celsius to reach its liquid crystalline state. This would be impractical for a television display, so the search for materials that could be operated over a broad temperature was conducted. In 1966, RCA chemists Joel Goldmacher and Joseph Castellano developed pneumatic liquid crystal mixtures that operated from below room temperature to over 100 degrees Celsius. Once liquid crystals with broad temperature ranges were developed, it was possible to build the first practical liquid crystal displays. This was accomplished in 1966 when George Heilmeyer, Louis Zanoni, and Lucian Barton fabricated the first liquid crystal display using the new materials. It is believed to be the first electronic device to use a synthetic organic material as the active element. After the display was demonstrated to the laboratory director, a team of engineers was assembled under the direction of Bernard Lehner. His team developed electrical circuitry to enable operation as a flat liquid crystal display that presented rudimentary video images using a dot matrix pattern. Further developments took place, and displays with multiple colors were also built by RCA's chemists and engineers.
Liquid crystals became useful for electronic displays because they offered very low power consumption, making it possible to develop portable devices. The second important feature of liquid crystal displays is their operation at low voltages, making it possible to build battery-operated products. In addition, very thin displays could be made with liquid crystals, offering product designers the opportunity to develop numerous products that did not exist at that time. Liquid crystal displays were also compatible with digital electronics systems, which were also being developed at that time. Finally, displays could be made in many different sizes and could be available in color. Between 1966 and 1968, models of some of the first commercial products that were expected to use liquid crystal displays were built. The photo on the left shows a model of the first digital clock that used a liquid crystal display. A model of the first digital calculator that used a liquid crystal display is shown in the photo on the right. The photo on the left shows a model of the first electronic shutter that used a liquid crystal device. When the button was pressed, allowing electricity to flow across the cell, the clear panel became opaque, blocking the transmitted light. It was envisioned at that time that electronic window shades could be built using this technology. Today, such electronic windows are indeed in use. On the right is a photo of the first digital electronic multimeter using a liquid crystal display. Note the large size of the meter. Today, some multimeters using liquid crystal displays are available in such small sizes that the whole unit can fit in one hand. After RCA reported on its development of liquid crystal displays in 1968, some of the first products using the displays were manufactured and sold by various companies beginning in the early 1970s. The photo on the left shows the inside of the first digital watch made with a liquid crystal display. Both the watch and display were manufactured by the Optal Corporation in Princeton, New Jersey. On the right is a photo of a small digital clock made with a color liquid crystal display. The clock was made by Stanley Electric Company in Japan using RCA licensed technology. After more than 40 years, models of both the watch and the color digital clock are still in operation today. During the 1970s, many other products using liquid crystal displays began appearing. By the 1980s, liquid crystal displays were being made by the millions. This resulted in the creation of many new products including calculators, medical instruments, digital thermometers, measuring instruments and computers. In 1983, the first portable computers appeared. They used liquid crystal displays with screens that were 8 inches long and 3 inches high as shown in the photo. In the 1990s, computers began appearing with full-color liquid crystal displays in large screen sizes and with much higher screen resolution. The photo on the left shows a Philips desktop computer monitor with a large screen, full-color, high-resolution liquid crystal display. The photo on the right shows an early IBM laptop computer with a large screen, full-color, high-resolution liquid crystal display. Following RCA's announcement of the first liquid crystal displays in 1968, scientists and engineers from around the world were working to develop ways to construct a liquid crystal television display. The difficulty was in developing the technology to fabricate thin film circuits that could be placed on the inside of the display glass to drive the individual picture elements. In 1983, engineers at Seiko Instruments in Japan were successful in this effort, and they built the first color television with a 2-inch diagonal liquid crystal display screen shown in the photo. During the 1980s and 90s, more firms in Japan, Korea, and China began building larger and larger color television displays with liquid crystals. After the turn of the 21st century, liquid crystal televisions became available in very large screen sizes and much higher resolution. The photo on the left shows a 45-inch liquid crystal television set introduced by Sharp in the year 2000. A flat-panel liquid crystal television with a 52-inch screen made by LG Philips in 2003 is shown on the right. Just a few years later, much larger wall-sized screens became available. This photo shows a liquid crystal television with an 82-inch screen made by Samsung in 2005. This photo shows a liquid crystal television with a 100-inch screen made by LG Philips in 2006. Today, the main use for liquid crystals is in displays for electronic products including computers, television sets, mobile phones, iPods, iPads, instrument gauges, thermometers, clocks and watches. Liquid crystals are also used for temperature sensors, in biological research and for chemical structure analysis. Liquid crystal display manufacturing has come a long way since the first products were introduced in the 1970s. These photos from 1974 show LCD watch displays being made in small batches and with a high degree of manual labor. Liquid crystal display manufacturing today is done in highly automated facilities. This is a photo of a clean room at the LG Display LCD manufacturing facility in Korea. The automated movement of large display glass for LCD manufacturing is shown in this photo from the LG Display LCD manufacturing facility in Korea. This photo from the LG Display LCD manufacturing facility in Korea shows an image of a large plate of glass with 9 patterned sections, each of which will be used to form a single display. Testing and final inspection of the displays are done using modern computerized equipment as shown in this photo from the LG Display LCD manufacturing facility in Korea.
In summary, the development of liquid crystal displays was the result of the need to develop a flat panel television set. The curiosity of scientists about little-known materials called liquid crystals. Experiments performed in physics, chemistry, and electronic engineering. The synthesis of new liquid crystal materials by organic chemists. And the ingenuity of engineers to build complex electronic circuitry and manufacturing techniques. This presentation was produced as a public service to help middle school and high school science teachers develop experiments, presentations, and demonstrations that can be used in their classes. More science experiments and demonstrations are available on the Tops of Santa Clara Valley website, www.topsofscv.org. TOPS, Teaching Opportunities for Partners in Science, is a program aimed at stimulating greater interest in science by middle school students.